Thank you very much for the introduction, and it's a pleasure to be back in London. So today I'm going to be talking about some joint work with Anna and Kim on how good is it really when we're using the worst case noise analysis when looking at FHE schemes. So obviously homomorphic encryption needs no introduction in this audience, but let me just quickly recall the main idea to get started. So in homomorphic encryption, we typically have a client and a server. The client is a data owner, but they're not very computationally powerful, and they want to compute a function f of x on their data x. But because they're not very powerful, they want to outsource this to a cloud server. However, they don't trust the server, so they're only prepared to share their data in an encrypted form. So here, encryption of x in the yellow box over to the server, along with, and they send also a description of the function f which they want to evaluate. So homomorphic encryption is basically all contained within this eval function, which takes as input an encryption of x and a function f, and its output is an encryption of f of x. And the server can generate this ciphertext encrypting f of x without needing to decrypt or otherwise having access to the secret key. So the server, once they've generated f of x, they can send it back over to the client has the secret key and can decrypt. So thinking about what such a function eval could do, it's clear that homomorphic encryption has many possible applications, and you're really limited only by the space on your slide. And what I think is interesting among all these applications is several of them, in fact many of them, are in areas which are outside of cryptography basically. So for example, genomics or machine learning. So what's really motivating our work is that the potential user of homomorphic encryption is not necessarily an expert in crypto, and so they might not necessarily know what the optimal choices are for setting parameters. So we're interested in noise analysis because it's going to be important for setting parameters for correctness. So here's a brief history of FHE, which I won't present all of, but just to say and to give a general context for the work that we're doing. So obviously FHE has been going now for 10 years since Gentry showed us how we can do it. And at that time it was completely a theoretical advance. There was no way to implement Gentry's scheme. But now, in recent years, we've made a lot of progress towards making homomorphic encryption practical. And yeah, this work is also playing into that. Because from my point of view, the most important thing to make it practical is to make it actually usable and to help users out with things like setting parameters. So some important steps towards this process, which I'll say a little bit more about on the next slide as well, is things like making open source libraries available, progress in bootstrapping, progress in encoding, from some of the people in this room even. And yeah. Recently, there's also been the standardization effort, which I think really crystallizes how practically relevant this technology is becoming. And now you're starting to see startups that are offering solutions based on homomorphic encryption, as well as interest from really large tech players as well. So I would say that we're far from the point of FHE being impractical, but we're now at the point where it's essentially commercially viable. And two of the main things towards practicality that we've seen recently are, firstly, open source libraries. So in this work, we're focusing on the FV and BGV schemes. So there are at least 3 actively maintained homomorphic encryption libraries that are either implementing one or both of BGV and FV. And in this work, we're going to be looking at the implementation of BGV in HElib, as well as the implementation of FV in SEAL. But note that also the Palisade library is implementing both of these. And as well, the work is kind of motivated by what's going on in the standardization effort. So this has been running since 2017. It's being done by a consortium of academia, industry, and government partners. And the first thing that the standardization consortium was working towards was standardizing a way to choose secure parameters. So they have now published a standard with a methodology for choosing secure parameters. And then, so the next thing that they've moved on to focus on is things like usability, applications, and APIs. And one of the things that's really being focused on right now is things like some kind of homomorphic encryption compiler, or tools like an automatic parameter selection tool that would help users to not have to choose the best parameters and the most optimal implementation methods themselves, but rather they would just type like x plus y, and then it would find a way to do the homomorphic addition of x and y in the easiest way possible. So our work on analysing noise and trying to do it like more tightly would really play into this kind of work of being the noise analysis component within an automatic parameter selection tool. That's really like, my ultimate goal would be to have automatic parameter selection. All right, so a couple of slides to say to remind you what noise is in homomorphic encryption. So if we talk about fully homomorphic encryption, this is like essentially what we would really want, which is a scheme that is supporting arbitrary computation on encrypted data. But we might also have somewhat or leveled homomorphic encryption, where we can support computation on some encrypted data up to a certain amount, so say up to a certain depth of circuit, or a polynomial up to a certain degree. And what Gentry showed us in his seminal work is that you can create an FHE scheme from an SHE scheme if you also introduce this process called bootstrapping, which is essentially homomorphic evaluation of decryption. And the reason why you would need to do this is because of the noise. So in homomorphic encryption, all ciphertexts have an inherent noise. It's something that they have to have for security reasons. They're born with it. They're born typically with a small amount of noise, and then as you move through homomorphic evaluation operations, the noise grows, especially after things like multiplication. So if the noise ever reaches a point where it's too large, then this means that decryption is going to fail. So obviously this is problematic because then you've lost all functionality. If the server sends you back a ciphertext which you can't decrypt, you've failed to outsource your computation. So it's really essential to understand how the noise is going to grow during the homomorphic evaluation, either so that you know when you want to bootstrap, or so that you can like work in this somewhat homomorphic or leveled homomorphic setting where you know how big the noise is going to be eventually, and then you can set your parameters large enough to support the computation which you want to do. So on the one hand, you obviously want to set things, parameters to be large enough to support the computation, but on the other hand, if parameters are large, this means it's computationally less efficient and it takes up more bandwidth, so it's kind of undesirable in that sense. So, and this is really one of the major challenges remaining in practical FHE. So, yeah, what we want is a way to make sure we still have correctness while making the parameters as small as possible. So, I'm now in a position to state what we've done in this work. So there are three main contributions. So firstly, what we're looking at is how effective is heuristic, or rather are heuristic worst case noise analyses in the FV and BGV schemes. So within that, so in Ilia's thesis, he gives a new way of obtaining these worst case heuristic bounds and presents them for FV, so we do the same analysis for BGV. And then we give evidence that these bounds are tighter than the previous method. And we do this by comparing with like what the heuristic bounds would predict the noise grows like with what the noise actually is growing like in BGV ciphertext as implemented in HElib and FV ciphertext as implemented in SEAL. And what we see is that although Ilia's method does give quite a dramatic improvement in some cases, there nevertheless remains a quite large, what we call heuristic to practical gap between what the noise, heuristic noise analysis predicts the noise will be and what the noise actually is. So we kind of propose an open problem and we give some discussion around why we think, well, our conjecture is quite strong, why we think that the heuristic worst case analysis can't be improved theoretically. Like just looking at a theoretical analysis of BGV, you're going to get a gap compared to, for example, the implementation in HElib. And then a separate thing which we do, also using Ilia's new noise analysis, is we're looking at the comparison of Costache and Smart from 2016 at CT-RSA. They compared several ring-based homomorphic encryption schemes, and we're looking at their comparison of BGV and FV. We redo this analysis using the new noise method and also by bringing up to date the security analysis and make some other improvements. And we actually find that FV appears to have a small advantage over BGV, even in parameter settings, which Costache and Smart found that BGV should be outperforming FV. All right, one slide on parameters. So I'm not going to define or recall ring algebra B for you, but I will be making reference to these parameters throughout the talk, so just to say what they are. So we have some ring algebra B instance parameterized by a dimension n. N is always going to be a power of 2 here. We're working with a power of 2 cyclotomic ring. We've got a ciphertext modulus Q, which is what a fresh ciphertext will be encrypted to, and this is formed as usual from a chain of moduli, which is each modulus in the chain is formed by a product of primes. We're going to have a ring algebra B error distribution. It's going to be a discrete Gaussian with standard deviation sigma. Sigma is basically going to be 3.2 whenever we need to specify it. And then we also need to state a secret distribution. We need a plaintext modulus T, and we're also going to want to have parameters that are a certain amount of secure, so we're using the homomorphic encryption standard for this, and that's parameterized by a security parameter, lambda. We're going to look at lambda equals 128. All right, so on to discussing about the first contribution of the work, so heuristic worst case noise analyses of FV and BGV. All right, so I'll firstly recall what we were doing previously, and then I'll introduce what Ilya proposes to do instead. So essentially what you want to do in this heuristic worst case noise analysis is somehow say something about if you've got a noise polynomial A, or a component of the noise A, say something about what the infinity norm in the canonical embedding of this noise polynomial A is. And so what we know about the polynomial A is its coefficients have variance V sub A. So if you just have A on its own, you can think that when you're doing this canonical embedding mapping to it, you end up with something which is like a sum of n assumed to be independent identically distributed things of variance V sub A. So the variance of that thing will be n times V sub A, and you can model it as a Gaussian because you're summing up n thing, and n is going to be like in the thousands. So then you can say something like, well, we know how the tails of a Gaussian behave, so with very high probability you're going to be within a certain bound of some multiple of the standard deviation of that Gaussian. So we can take, for example, the bound 6, and if you say that canonical embedding of a infinity norm is less than like 6 times standard deviation, then you can see that that will be equal to 6 times square root n times square root V sub A. And the kind of reasoning behind the choice of 6 is because of this ERFC function being very, very small. So this is corresponding to a very, very low probability that this random variable will fall outside of that range. When analysing the noise as well, you might need to look at what's happening with a product of polynomials A times B. And in this case, kind of the key takeaway point is that the product is done in the canonical embedding. So you then would take the bound 16 times n times standard deviation of A times standard deviation of B. And the logic behind this is, well, okay, let's take the bound 4 now for each of A and B. Again, you can say something about I don't know how to pronounce this function, ERFC of 4 is like 2 to the minus 25, so both of them together would be like 2 to the minus 50. So again, it's a very low probability that the product AB, when seen in the canonical embedding, will be outside of this range. So in contrast, what Ilya proposes is do the analysis of the variance in the ring and then go into the canonical embedding. So even when you have a product, for example. So if we have like polynomials A and B with variances of the coefficients VA and VB, we can say something about like what the variance will be of polynomials A plus B, a scalar multiplication of A, or the product of A and B, which are given like this. So you can use these relationships which we have on the variance to work out what the variance of the whole noise polynomial would be, and then map it into the canonical embedding view like this. This is the same bound as we had before. So I want to illustrate that with an example. So we'll do fresh ciphertext in FV. So first I'll recall what FV ciphertext look like, what the definition of noise actually is, and then we'll see how to bound it. So as you may recall, in FV, a ciphertext is formed of two components, C0 and C1. And the C0 part is, firstly, you take the message and then you scale it up by essentially the ciphertext modulus divided by the plaintext modulus. And then you add on some stuff that's supposed to look like a ring-LWE sample so that you can have security. So you firstly choose an ephemeral secret U, and then you add the first part of the public key, which is itself a ring-LWE sample, and you add a ring-LWE error. And the second part of the ciphertext is just a ring-LWE sample, basically. So the secret is this ephemeral secret which we sampled. The A is the A from the public key, and you add another ring-LWE error. So when you want to decrypt such a ciphertext, or indeed any FV ciphertext, you firstly multiply the C1 part by S, and then you add it into the C0 part. And what this is going to do is get rid of these A times U times S terms. So you're left with scaled up thing of the message plus essentially noise. Then the message has been essentially scaled up by Q over T, so we need to times by T over Q to just recover M. This is going to make the noisy parts really small because Q is typically much, much bigger than T. So we just round off to get rid of the noise, and then we interpret the answer mod T. Oh, because, yeah, the message is only defined up to mod T. T is the plaintext modulus. So the definition of invariant noise in FV is exactly this. So if you look at a partial decryption, T over Q times C0 plus C1 times S, then the noise is V where that thing is equal to message plus V plus some multiple of T. And the intuition of this noise definition is that if this noise isn't removed by the rounding, that's the point where decryption is going to fail. All right, so it's not hard to see that if T divides Q, so we don't have some kind of rounding term from the dividing to bring Q over T times M down to just M, then the noise in a fresh FV ciphertext will be given by this, so T over Q times some terms depending on the ring-LWE error distribution and the ring-LWE secret distribution. So in a previous method of bounding this, you would simply take norms on both sides of this equation and then use a triangle inequality, and you'll arrive at an expression like this. So now we use the method discussed on the previous slide. So we have firstly to bound a term that looks like a product of two terms where we know the standard deviation of one is like sigma and the other is like, assume that the secret is uniform ternary, then we also can write down the standard deviation. And we just use this bound of 16 times n times the standard deviation of the error times the standard deviation of the secret. Then here we just have a term that's just one polynomial on its own, so it's 6 times square root n times its standard deviation. And then this term behaves exactly like this term. So this is the result you would get, and then obviously you can simplify it a little bit. And here I've written it in this format in order to compare it to what Ilia's method is going to give us. All right, so what Ilia is suggesting that we do instead is, okay, here's the noise polynomial. What would its variance be in terms of the variances of E, U, and S, and so on? And you would get this. And then simply we're going to use 6 times square root n times square root of v sub v, which gives us this expression. And kind of ignoring the plus 1 for a moment, this is roughly like square root 4 over 3 times square root of n times this term that's the same as before. Whereas here we've got 16 times root 6 over 9 times root n. So this is 4.3-ish. This is 1.1. So you can see that this is already going to be better. And we'll give more evidence of it with the experimental data in a moment. All right, so we want to compare with how the noise grows in HElib and in SEAL. So how do we actually generate data? Well, we're going to have 10,000 trials of this particular experiment in HElib or in SEAL. So in the ith trial, we're going to generate some fresh ciphertext encrypting I and I+1. we're going to add them, we're going to multiply the result with one of the initial fresh ciphertexts, and then we're going to modulus switch the result of that. And after each of these operations, we're going to measure what the noise is in the ciphertext. In fact, we're going to measure what the noise budget is. So noise, because, for example, in FV, the noise is like scaled by T over Q, and Q is really, really small, so you don't want to look at something really, really small. You can instead like kind of scale it up again and view it as like, how much space do I have left to do operations within the ciphertext? And you can define a similar operation for BGV and implement it in HElib, which is what we've done, to make it easier to compare between the results from SEAL and the results from HElib. So anyway, after we've done each of these steps, we record what the current noise budget is, and at the end of this whole thing, we'll output the average noise after each operation. And then on the other hand, we're going to look at what the noise growth would be using these worst case bounds given by Ilia's method and by the previous method. All right, so here's the results for BGV. So giving the heuristic bounds and the observed noise, average noise in HElib. So the column P is previous bound, column I is Ilia's bound, and the column X bar is the mean observed noise budget. And then each row is a different parameter set. So we're, again, using these power of 2 cyclotomics. So we're going from the parameter set with n equals 2048 up to 16384 here. And okay, what can we take away from this slide? Well, firstly, importantly, we can see that both of these kinds of bounds do indeed work. So they predict that there's more noise in the ciphertext than there actually is, and hence less noise budget than there actually is. So you could go ahead and use these bounds to set parameters, and you would find that things would be decrypting correctly at the end. And what you also notice is that looking at the column of Ilia's method, it's closer to the actual observed noise than previous methods, as you expect. And so this is giving a better model of the noise than we previously had. Nevertheless, there's still quite a large, what we call heuristic to practical gap between what the bounds predicts and what you see in the ciphertexts. And you can also notice that the gap kind of tends to increase as n is increasing. So, yeah. So the results for FV compared with the implementation of SEAL give a very similar picture. And really the only difference to highlight is that, for example, if we look at the multiplication bounds, here we see like quite what a dramatic improvement using Ilia's method does give you. So this is saving you 10 bits of noise budget, basically. So it's very nice, but nevertheless, you still have this quite large gap between what you see in practice. So, yeah. Basically, the conclusion is this does work as modeling the noise, but the gap still exists. So I want to say a little bit more about this heuristic to practical gap, because what we're conjecturing is you can't improve it theoretically, and I'm going to present some evidence for that, of like different things we tried to improve it and why it is they're not working. All right, so the first thing that we thought about was like maybe the notion of noise is wrong. So here's an observation about FV. So as we talked about before, the FV ciphertext satisfies if you do C0 plus C1 times S, you have like essentially Q over T times the message plus some noisy parts. But then when you decrypt, you multiply this by T over Q. And so say T doesn't divide Q exactly, you're going to get this kind of rounding term, which is only being introduced during the decryption itself. It's not in the ciphertext before they're decrypted. But by definition of invariant noise, it's always including this rounding term in the definition of the invariant noise. So even like if you have some ciphertexts that are not at the end of the computation, you're going to continue computing on them. But when you measure their noise, you're reading off a noise that's more than it actually is. So we thought, like, what about if you define the noise so as not to include this rounding term? Or this, if you like, noise introduced by decryption. So we implemented this in SEAL and had a look at how this definition of noise was growing compared to what the heuristic bounds would predict, and we actually found it was still very similar, no significant improvement than the previous method. So another thing to observe is that when you're looking at a worst case analysis, like loose bounds are somehow a little bit inherent. So at the end of the day, what we're trying to do is bound a Gaussian in the canonical embedding. And so like this is exactly the equation we're using. Like if we have, well, this should be a sub v here, sorry about the typo. But yeah, it should be less than some bound times square root of n times whatever the standard deviation is in the coefficient space. And we said that we're using b equals 6 because of this property of ERFC of 6 is very small. And of course, we want to assure, if we're like writing down a formal bound, we want to assure that like things are going to be correct with like some extremely high probability. But of course, in practice, like we're only like generating like 10,000 ciphertexts. It's very unlikely that we're going to encounter one with such a large noise, and indeed we didn't. So it seems like when you have to choose such a large B, you're always going to have this inherent looseness. And even if you tried another way to like view the noise as a Gaussian in the canonical embedding, which is what we've been doing in a separate work with Sean, you still are going to run into this issue. So Ilya posed me a nice question the other day. What about if we chose some different B? Like, could we get any better? So here are some results for SEAL for fresh ciphertexts compared with what heuristic bounds would predict if you chose a different choice instead of b equals 6. So you can see that even when you choose b equals 1, in various parameter settings with different kinds of encoding, you still observe a gap. And I think b any less than 1 would be kind of bizarre, right? Because then you're only saying you're within one standard deviation. So probably with reasonable probability you would be outside of this. And even then you still have a gap. So you could think like, okay, well, that's just a fresh ciphertext. Like maybe it's also interesting to consider other kinds of ciphertexts. So here are some HElib results. Firstly for a fresh ciphertext, but then also for like the ciphertext that's a result of that operation I described from the experiments earlier. So you do adding, then multiplying, then finally a mod switch. So what can we see from these results? Well, if we look here at the n equals 8192 result for the ciphertext after mod switching, with b equals 1, it looks like, oh, this is a pretty good match for what's really happening. But if we were to go down to the smaller n, we see that we're actually predicted more noise budget than we really have. And in fact, we actually have this with b equals 6, which is a little bit alarming. So what this is saying is there doesn't appear to be a way to even select a smaller b that's going to be true across all operations and across all parameter choices. And yeah, for example, if you have b equals 1 in fresh ciphertexts, you again still see, in some cases, a quite large gap. And then another thing, which an anonymous reviewer suggested to us, is like, what about if we had an average case analysis for the noise instead of the worst case? Because clearly, like, we're comparing like an average observed noise with this worst case kind of bound, so you might expect there to be a gap. So the TFHE scheme, for example, has a very nice average case approach, which I think is a really, really nice noise analysis. So what's happening there is that the noise coefficients are always being modelled as independent sub-Gaussians, and you just trace what is happening to the variance throughout the computation. So the fact that you could model them as independent sub-Gaussians, this is a heuristic assumption, but it was experimentally verified for the gate bootstrapping operation in their paper, which I cite below. And the thing with TFHE is every elementary operation can be implemented with gate bootstrapping on a linear combination of ciphertexts. So this means that whatever you're doing in TFHE is somehow linear. So then you can easily write down, like, the noise is always going to be sub-Gaussian. If it's sub-Gaussian in this case, it's going to remain sub-Gaussian. So everything goes through really nicely because it's linear. But an issue that we see is that in BGV and FV, we have nonlinear multiplication operation. So it's not clear that things will remain sub-Gaussian. So I think this would be a nice direction for future work, but it might be trickier to write down what the distribution is. All right, so some words on our comparison. So firstly, it's just to say it's very natural to want to compare HE schemes. You know, like, especially if you're the application developer, you might be like, okay, well, I want to build this application of homomorphic encryption, but like, which library shall I use? Which scheme shall I use? So previous works have tried to compare different homomorphic encryption schemes. There was a comparison of FV and Yashi by Lepois and Neyrig in 2014, and then in 2015, Kim and Lauter compared BGV and Yashi. And the starting point for our work now is Costache and Smart's 2016 comparison of all the main ring-based FHE ones at the time, which was FV, BGV, Yashi, and LTV. And we update this comparison in several aspects. So firstly, we in our comparison, we choose parameters that achieve security level 128 according to the homomorphic encryption standard. In contrast, Costache and Smart chose parameters according to linear Picot's analysis, which is now known to be inaccurate. We use Ilia's noise bounds, so update the noise heuristics within the comparison. Our comparison allows for a more flexible modulus switching, and we're no longer considering these entry-based schemes Yashi and LTV because of their vulnerability to these overstretched parameter attacks. But what we're actually doing is essentially the same thing as the CS16 comparison was doing. So we basically want to find the minimal parameter set that supports a certain operation. So we try a parameter set with a certain dimension n, a certain chain of moduli, and a certain standard deviation. We generate some fresh ciphertexts, and then we're going to do a leveled computation where at each level what we're doing is zeta additions, then a multiplication, then a relinearization, and then we go in modulus switch down to the next prime, and so on. And then when we have modulus switched at the final prime, we check if decryption was successful. And if it was, we're good, and if not, we try again with a larger dimension. So yeah, what's our goal here? So we've got a circuit that's parameterized by zeta additions and some depth L. And if we have a fixed such L and a fixed plaintext modulus and a fixed level of security to determine the other parameters, the goal is what is the smallest parameter set such that decryption will succeed. And smallest in terms of the ciphertext size in kilobytes. So this is important, for example, for bandwidth. So it's like which scheme is best when best is viewed in this sense. We look at 3 different plaintext moduli to compare with the CS16 conclusions. So in the first, plaintext modulus is t equals 3, and this is a setting where CS16 concluded that FV should outperform BGV. Then we try t equals 256, which is a point kind of at the crossover in the CS16 results. And finally, we have t equals 32768, and this is a plaintext modulus that's beyond the crossover point, where CS16 reports that BGV is outperforming FV. What did we choose for the other parameters? Well, we set zeta equals 8, which was what was also chosen in CS16. We, as usual, do sigma equals 3.2 for the error distribution. For the secret distribution, we're assuming uniform ternary secret for both BGV and FV. So this is ensuring that the comparison is fair, and it's also now the default parameter setting in both HElib and SEAL. So we think it models well what's going on in practice. We're using power of 2 cyclotomics from n is 2048 up to 32768. And then to determine the chain of moduli, we make sure that the top modulus is conforming to the security level lambda equals 128 according to the standard, so we just use the standard bit length of Q. And we look at the results for a range of intervals between 2 and 30. Now, I present the results here, but 30 got cut off at the end of the slide, so you'll have to trust me that the results are what you would expect for that level. Okay, so each table is the results for the different plaintext moduli that I mentioned, and it can be viewed broadly as wherever it's not highlighted, BGV and FV seem to be performing the same. That is, the minimal ciphertext required, size of ciphertext required was the same. But in the highlighted cases, FV supports the computation with a smaller set of parameters than BGV. And that's true even at these larger plaintext moduli beyond the crossover point where BGV was said to outperform FV in CS16. A good question was posed to me earlier by Nigel, which is, well, you know, is there a crossover point that's just with larger T? And the answer is, I will check that later. It's a good question. But yeah. So let me make some concluding remarks. So the conclusions from our updated comparison with CS16, firstly, what we can see from this table is essentially BGV and FV are pretty much the same in a lot of cases. So it shouldn't be the case that someone who's deciding what to do should be like strongly preferring BGV or FV compared to one another. However, it is the case from our results that sometimes FV is outperforming BGV, even for plaintext moduli that are larger than where it was said to outperform BGV in CS16. And then some conclusions from the previous part of the talk. So the Iliashenko bounds are tighter than previous methods for generating worst-case heuristic bounds of the canonical embedding norm. But nevertheless, we do see a large gap compared to like ciphertexts in practice in practical implementations of FAG. We conjecture that this worst-case gap can't be improved theoretically for some of the reasons that I described. And what we think would be a good direction for future work is looking at a kind of analysis that's implementation specific. So one observation is that in, I think, both HElib and SEAL, things are implemented in this kind of CRT-like representation, so you're never working with just one ring element, you always have several for each ciphertext, so perhaps this is impacting on the noise in practice. So we do have an earlier version of this work available on ePrint, along with the code to reproduce the experiments. We recently resubmitted a quite heavily updated version of this work, and I hope to have the new version on ePrint very soon, and thank you for your attention.